Hi guys. So we talked about how to classify matter before. Now we're going to continue talking about matter. This is going to be a little bit more of a review, but it's been a minute, so we're going to review it together. We're going to be talking about properties and changes of matter. So we've classified matter. Now we're going to talk about how it can change. So all elements and compounds have characteristic properties, and those properties can be classified as either intensive or extensive. So here's the difference between those. An intensive property does not depend on how much matter is present, but an extensive property does depend on how much matter is present. Okay, so get those definitions copied down, because that is actually kind of the important thing here. So an intensive property does not depend on how much matter is present. Intensive properties are kind of characteristic to the type of chemical you're talking about. So for example, water is clear. That is an intensive property because water is always going to be clear no matter how much you have. An extensive property depends on how much matter you have. Okay, so like mass. If you have a bigger sample of something, it will have a greater mass. Okay, so let's come up with some examples. We're going to start with intensive properties. Sorry, my handwriting is not the best. Okay, so intensive properties. Let's come up with some examples of those. So I already kind of gave one sort of example when I said water is clear. We can actually expand that to include color in general. So the color of something is characteristic to that chemical. It's not something that really depends on how much you have. Water is always going to be clear. Sugar is always going to be white. Copper's 2-sulfate is always going to be bright blue. That's a fun chemical. So the color is something that you can actually look up for each chemical. Sorry. All right, so color. Another thing that you can, that is an intensive property would be like density. Densities of different substances are things that you can actually look up. So the density of water is usually 1 or about 1 gram per milliliter. The density of aluminum is 2.7. You guys know I have that one memorized. I don't know why. You probably will too, just because of me. But the density is always going to be the same for a chemical. It doesn't depend on how much you have. It depends on what it is. Another example would be like just general reactivity. Some chemicals react more than others, so that is something that is intensive or depends on the chemical's identity. So something like gasoline, we know is extremely reactive, especially if you ignite it. It contains a lot of energy, and that's just something that's characteristic for gasoline. But then if you're talking about water, water is a little bit more stable. It can react. All right, it's not like it doesn't react, it does. But it's not nearly as reactive as some other chemicals, which is probably a good thing because we have oceans full of it on our planet. Okay, so extensive properties. These do depend on how much you have. So the example I already gave is mass. Another example would be like just general size or volume. So volume, how much space something takes up. That is going to get bigger if you have more of it. So that is going to be an extensive property as well. If you're talking about like copper wire, that would be length. And then this one's kind of a weird one. Let me explain it. Energy. So imagine you have like a small spoonful of gasoline, and then you have like a giant bucket full of gasoline. Which of those is going to contain more energy, just in general? Which one can power your car for longer? Obviously, the spoon, there's less, so there's less energy. The big bucket full of gasoline, that has more, so it would be more effective at fueling your car. So the more of something you have, the more like internal energy it has. Okay, so hopefully you see the difference between those two. We can actually continue to classify these properties. We can classify them also as physical or chemical properties, and you've probably seen these terms before. So a physical property is a property that can be observed or measured without changing the identity of the substance. So in other words, these are things that can be observed using your five senses. So, your sight, smell, taste, hopefully not taste, if you're doing chemistry. Sound doesn't really apply to matter that much. And texture. So those would be physical properties, anything that you can just like physically observe about something. Or something that can be measured. So think about things that that can be measured. So you can measure the mass of something. You can measure the volume of something. You can measure the temperature of something. And then, of course, anything that you can calculate out of those measurements. So density is also a physical property because it can be calculated from two other physical properties. And we'll talk more about that in a second. A chemical property, on the other hand, is something that relates to a substance's ability to react or transform into a different substance. So anytime a chemical reaction occurs, that's going to be a chemical property. So how reactive is something in certain situations? So things like flammability. When something catches on fire, it's reacting with the oxygen in the atmosphere. So that is a chemical property. Also, ability to rust. Rustability is not a word. Why don't we say like overall reactivity? Some chemicals are just going to be way more reactive than others. And then on the flip side of that, some chemicals are just like not reactive at all. So we're going to learn more about which chemicals do that, but the noble gases and a lot of metals don't react with very much at all. They're kind of stable where they are. So those, we call that inert. When something doesn't react, it is inert. So inertness is a chemical property as well. So anything that describes how something could potentially react. Okay. So those are properties. Let's talk about changes next. So I want to talk about physical and chemical changes. It's very similar to chemical and physical properties. Let's start with physical changes. So I actually have a definition for this. A physical change is any change matter undergoes that does not change its identity. So if you start with water, after the physical change, you will end with water. It doesn't change what it is. It just changes kind of how it appears or maybe its state. So let's talk about some physical changes. One, sometimes you have like a big giant crystal of something and you grind it down into a powder. That is going to be a physical change because you haven't changed what it is, you've just changed how it looks. So grinding into powder is a physical change because it's still the same chemical. Another physical change would be like tearing or ripping. Another physical change would be basically any phase change that you can undergo. So an ice cube melting, that would be a physical change because ice is solid water and it melts into liquid water. Solid water and liquid water are both water, so that is going to be a physical change. Okay, any phase change. Chemical changes, those we are going to be spending a lot more time on in this class because those are basically the crux of chemistry. So a chemical change is any time you have something that does change from one substance into another. So crazy important in chemistry are the chemical changes, go figure. So a chemical change, any change that changes the identity, it's an S, of a substance. And one thing about chemical changes is that they do come with a chemical equation. These can be represented with a chemical equation. Okay, so an example of what a chemical equation looks like, and again, we're going to talk about this more in the future, I just kind of want to show you what it is, would be like if you had methane and you were burning it in oxygen. After you burn it, what you have afterwards is carbon dioxide and water. And this does need to be balanced, but again, we'll talk about that in the future. That's a chemical equation. So if you take a look at that chemical equation, you can see we start with CH4 and O2. So methane is 1 carbon and 4 hydrogens. Oxygen is just O2. And you end with CO2 and H2O. So you end with carbon dioxide and water. So you've actually changed the chemicals from methane and oxygen into carbon dioxide and water. They have changed their identity into 2 completely different substances. So that is a chemical change. It is a different substance. Chemical changes also have a lot of characteristics. I guess I can write those off to the side in this blue square that I don't know what it is. They have a lot of observable things that generally happen. And of course, every chemical reaction is different, so it's not like they're all going to do the same thing. But some things you can see are color changes. So I guess you guys won't, but usually we do a lab in chemistry where we react iron with copper 2 sulfate. And what you start with is an iron nail and a bright blue liquid. And then after a day passes, you leave it overnight, you come back the next day, it's a yellow liquid with a whole bunch of solid copper. So there's a color change. It goes from a blue liquid to a yellow liquid. Any kind of bubbling? Bubbling, not always, but usually indicates a chemical reaction. One really famous exception to that would be like if you put Mentos in Coke, you know, it kind of shoots up and creates like a big geyser. That's actually technically a physical change. All you're really doing is taking the carbonation out of the soda. You're not actually doing a chemical reaction. So because of that, because all you're doing is taking something from being dissolved to not dissolved, it's still carbon dioxide before and after, that's actually a physical change. But bubbling usually means a chemical change. Let's see what else. Anytime you produce an odor, or I guess a new odor. A lot of chemicals have kind of a characteristic smell. So if you create a new chemical, sometimes you can change the odor that is being generated from those chemicals. And then also light and energy. And on that note, let me show you this sweet video I found. Okay, so when you're looking at this video here, let me see if I can play it. Maybe. It's working before. Why is it not working now? I have an idea. Hold on. If I do it here. There we go. All right, so go ahead and watch this video. Okay, so you can see here you start with a black powder, and as they introduce oxygen, you can see a ton of heat and light is being generated, just lots of sparking. And what you're left with is just kind of like a black test tube. So that's actually pyrophoric iron. They generated it by decomposing an iron compound into, I think it's iron oxide. I think that's what that pyrophoric iron is. Pyrophoric is actually a word that is often used to describe anything that self-ignites. So anything that catches on fire just when it's exposed to air. Actually, I did do a lot of chemistry with pyrophoric chemicals before I came here to Hayes. So it's something that's near and dear to my heart. I've actually caught myself on fire probably like 5 or 6 times. All right. So the last thing I want to talk about, which I think there might be something after this. Okay, so I want to talk about density. So density is a measure of how closely packed the atoms and molecules are in a substance. We've seen a little bit about density when we were doing dimensional analysis. We had some calculation questions that had density in them. Density is just measuring like how close together the atoms and molecules are. So if you were to look at a sample of a substance and just like zoom in really far so you could see the atoms and molecules, how much space is in between them? Are they really close together so that they're almost touching, or are they really far apart? Density can be calculated. It's actually a calculation. It's a ratio. It can be found by measuring an object's mass and its volume and dividing them. So in other words, the density of something is the ratio of its mass and its volume. Let me go ahead and actually write that equation down off to the side because I can't remember if I did. Density is mass over volume. An object less dense than its surroundings is going to float. An object more dense than its surroundings will sink. So like if you think about a helium balloon, helium has an extremely low density. So anytime you fill a balloon with helium, it has a smaller density than the surrounding air. And so the air actually kind of pushes it up. And that's what causes helium balloons to float. This is also why a lot of things float in water, because water has a density of about 1. So anything that has a density smaller than 1 is going to float. Anything that has a density bigger than 1 will sink. Shape and size don't affect the density of a substance because it is a ratio. As you have more of a substance, the mass and the volume both increase at the same time, so the density, the ratio of them stays the same. However, temperature actually can affect the density of a substance. You can see this more for gases, but it is true for everything. So you can take like a solid block of iron and heat it up, and it will change its density just by a very, very small amount. So for example, if you're talking about water, and this is liquid water, so we're not even talking about a gas here. Water at 15 degrees Celsius has a density that's 0.99099, 0.000, gosh, numbers, 0.999099 grams per milliliter. Water, however, at 30 degrees Celsius has a density of 0.995646 grams per milliliter. So you can see by increasing the temperature of the liquid from 15 to 30, so it's a little bit hotter, you can actually decrease the density just a smidgen. Now, for all intents and purposes, it's not really going to change it very much at all because water is a liquid at those temperatures and at just normal ambient pressure. So because it's a liquid, it's only going to change a tiny bit. But if you're talking about like very, very precise calculations, it actually becomes kind of important. All right, so here's what's happening with the density. So you can see here we have a low density substance, and here we have a high density substance. If you were tracking the temperature, go back. Yeah. If you were tracking the temperature of those substances, as you add energy to something, the molecules are actually going to get a little bit farther apart. So over here, this would be a high temperature. Because you've added energy to those substances, they're moving a lot faster. They're actually going to spread apart a little bit more. And then at a low temperature, they're going to kind of cling together. This is also why hot air rises, because hot air has a lower density, and things that have a lower density than their surroundings are going to float. Okay, so there's the equation that I was talking about. So density is mass over volume, or in short form, D equals M over V. So a pretty simple calculation. It's just a ratio that you have to take. Let's talk real fast about units, though. So units for density, because you're dividing mass and volume, it's always going to be grams per milliliter, typically in a normal chemistry lab. So this means that your mass needs to be in grams, and your volume needs to be in milliliters. Now, this is not always going to be the case. There will be problems that you see that the units are slightly different. So you do not have to change the units unless it asks for units to be in a specific way. Okay? All right, so the last thing I want to talk about is conservation of mass and conservation of energy. Now, these are two scientific laws, which means they are totally accepted as fact, as well as they allow you to make predictions about certain situations. So all changes, chemical or physical, will not change the amount of matter of chemicals present. So this is the conservation of mass. This is supposed to be an arrow. So let's say I have this chemical reaction right here. Let's say I start with 8 grams of hydrogen, 64 grams of oxygen, and that actually says 72 grams of water. So if you look at the total that I started with before the reaction took place, I had a total of 72 grams of chemicals total. 8 grams of it was hydrogen and 64 grams of it was oxygen. But when you add those two numbers together, you do get 72 grams. So you can see the total amount of matter actually didn't change with this chemical reaction. We started with 72 grams and we ended with 72 grams. The only thing that changed was how those grams were distributed. This is called the conservation of mass. Sorry, I know it's kind of being covered up. So this is the conservation of mass. Get rid of that. There we go. So conservation of mass states that all changes will not change the amount of matter or number of grams of chemicals present. This also holds true for energy. So it's not just true for mass, it's also true for energy. Anytime you have a chemical or a physical change, you cannot change the total amount of energy present. Energy can go from one place to another, so one chemical to another chemical, or it can be changed into another type of energy, which means it's transformed, but the total amount of energy is constant. So this is a conservation of energy. So let me give you an example of the conservation of energy. Let me get back to where I was. Okay. Gosh. Okay. Finally. So let's say I have gasoline and I'm burning gasoline. So this is going to be a chemical change because burning is a chemical change. Sorry. So burning gasoline actually does not change the total amount of energy present. That's actually a common misconception at first because a lot of people think about what burning gasoline looks like Usually it results in a huge amount of fire and light and just like a general explosion, but you're not creating energy. All you're doing is taking the energy stored inside the gasoline and you're releasing it as heat and light. So the energy stored inside a chemical is called chemical potential energy. And when you undergo that chemical reaction, you're just turning that chemical potential energy into heat and light. Okay? So you're not creating energy, you're just taking it from one form to another. And that's the conservation of energy. You always have the same amount of energy before and after a chemical reaction. All right, so that's it. That's all I have for you guys. Go ahead and get started on the assignment. Bye.